Now in section 2.2 we will discuss the divergence and curl of electrostatic fields. As we have already established the concept of electrostatic force, which we discussed in the Coulomb's law, and then from that electrostatic force we defined a field of a single charge, and the other interacting charge we considered is the test charge. Now as we are having the electric field, and the electric field is equal, like when we are having the source charge at the origin, then electric field is equal E 1 over 4 pi epsilon naught and the source charge Q over R square and R unit vector. So this is the electric field when we are having the source charge at the origin. Let me discuss some interpretations of the field lines, the electric field, and so on. For example, if I consider a charge, and this is a charge which is a positive charge here, then this charge is having field, electrostatic field around it, and we represent that field geometrically with some lines. Now these lines are actually not there, but this is a geometrical representation of the field which is around it. And also these lines are not finite lines, like we draw only few lines, while there are infinite number of such lines. These lines are showing the field. This is the geometrical representation of the field we are having for the charge. This is just like ray diagram when we use the optics, the lenses, and we draw some lines. So these lines, there are some properties associated with it. If we are having a positive charge, then the field lines will be diverging from it. You can draw as many lines as you want. They will be concentrated at the center, and as you go away, their distance will increase. These lines will never cross each other. They will never go over each other, and they are diverging to infinity. More the source charge is, more will be such field lines which will show the intensity of the field. And if we will be having a negative charge, and negative charge is like this, then we will represent it with the same field lines, but now the field lines will be, instead of outward, they will be now inward, just to show the convergence, the opposite of divergence. And the same lines are here, they are converging lines, and for a negative charge they are like this. So when we have a positive charge, then we are having diverging field lines. For a negative charge, we are having converging field lines. And another thing, that when these two charges will be in interaction, here we don't consider any interaction between them, but when these lines will be, these charges will be close enough. For example, I am having this is a positive charge and this is a negative charge, and now they are in interaction with each other. Then the field lines will be from positive to negative. This is a representation that the field is from positive to negative. Another line which will be from here to here, and as this is in electric dipole, now when we consider this line, there will be, whenever two charges are in interaction, then their field lines will never be in the form of a straight line. They will be curled. So if I look at this line, then this line we say that its curl is infinitely small. This is very small curvature of this line, while the next line, which will go from here to here or from here to here, will be very curved one. And similarly the other line, which will go from here to here or here to here, then this will be curved as well. And similarly the other lines, like another line will be like this and like this. So these are, the curvature will increase as we go from here, and when I reach here, then maybe some lines which are hard to draw from here are from here, then these lines are actually going in this way and they are reaching here this way. So they are, this is another representation that these lines are curving as well, and they are like this. If I consider another line, then it will be like this, like this. So they are going here and then coming over there, and similarly this line as well. And on the other side I can draw them like this. So they will be curving around. Similarly, this line, which seems to go straight, or here it from there it is coming straight. Now for these two lines we consider that their curvature is too huge, that for the small length we are having almost a straight line. So this is what we are having, the representation of two interacting charged particles. And when we will be having, instead of positive and negative charges, if we will be having two negative charges or two positive charges, like this is a positive charge and we are having another positive charge, then their field lines will be repelling each other, and they will be like this one, that from the central line will now be absent, and then the next line that we will be having will be starting from here. This is the center, and here this is the center. So it will be something like this. There will be no line which will be touching the central line, but they will be just going to infinity along this central point and like this. So they will be repelling each other instead of attraction, because they are the like charges. For both two positive or two negative charges, we will have the same situation. So here like this and like this, similarly like this, and we can draw as many lines as we want. Nonetheless, these lines as well as these lines or these lines, they will not go over each other, they will not cross over, and similarly like this and like this and so on. So we will be having then some lines like this and here, while some lines like this and here. So they will be like this, going this way, going away from it, and they are just here like this, going away from them. And then the more we go closer to it, the more the field lines will be concentrated here and here as well. So this is the representation, this is the geometrical representation of two line charges. Now if I will consider the electric field of this charge will be, this is charge, if this is charge Q, then the electric field will be equal to this one. While the same charge but minus Q, then this electric field will be replaced with a minus charge, like plus and minus. And when we are here, then here the electric field will be the electric field of this one plus the electric field of this one. And if these magnitudes are equal, for example Q and Q, and they are having let's say Q prime and Q prime, and their field individually is equal to E prime, then we will have the total electric field here at the center will be equal to 2 times the electric field of each. And the same, this is plus Q, so we are having plus Q here, and this is plus Q. So the electric field at the center we will be having Q minus Q. This is E prime minus E prime, and this is 2E prime, but this is E prime minus E prime, and this will be then equal to Q prime and Q prime. In E prime, the electric field of each is repelling each other. Here this is E prime minus E prime, so this becomes 2E prime, and here this electric field will be E prime minus E prime and will be equal to 0. So the electric field will be 0 over there. Now as we are geometrically representing them, so when we consider field around them, then that field is having some strength. And when we consider the geometrical lines, then how many geometrical lines are passing to a certain area, and that thing we call is electric flux. So this is electric flux. Now we know about flux. It may be electric flux, magnetic flux, it may be the air flux, light flux, or water flux. So any physical quantity or any amount of flowing thing or passing thing to some area, and that area is supposed to be cross-sectional to this one. So in order to measure how many field lines are passing through a given area, it depends on two things. Like if we will be having the more strength of the electric field, then there will be more field lines passing through a given area. And another thing is, it depends on the area as well, because it depends on the area. If it is cross-sectional to it, like the direction of the field line is in the same direction of the area. When we say cross-sectional, we say the area is perpendicular to it. But when we talk of the area direction, then the area direction will be parallel to it. So these two things are different things. They are not to be confused. Cross-sectional area means perpendicular area. And when we say the direction of area, so the direction of area is always perpendicular to a given surface. So that surface means the direction of the area will be along the field lines. If this will be the situation, then we know that maximum flux will pass. And if we will turn this area element or this area, then what will happen, that the flux or the lines passing through them, if they are here or here or here anywhere, the flux lines passing through them will decrease. And if we turn the area exactly like this and lines are coming from their direction, then none of the line will be passing from this area, and here the area is no more cross-sectional to it, but if we look at the direction of this one, then this direction is perpendicular to the direction of electric field, and we will have zero situation. So I say that if I talk in terms of the angle, if the angle will be 0 degree, means the angle between the electric field lines in the direction of the area, if this will be 0 degree, then we know that the flux passing through it will be maximum. And if we will have theta equal to 90 degree, like the area direction is perpendicular, the area direction is perpendicular to the field line, then this will be 90 degree and we will have the minimum flux, which is in reality equal, this minimum is equal to 0. Maximum can be any number, it will be a number, it will not be having the direction, it will be just a magnitude, a number, and we will represent it with two physical quantities here, like one the electric field and the other the area. So I can write, then the question arises, for example, if around this surface I consider a sphere, if around this surface I consider a sphere, then how much means so many field lines are here, I will consider a unit area here on this surface, and this unit area, it will be having the electric field lines in this direction, this is the electric field line, while its area may be having this direction. Now in this situation, although the direction means when we consider this is spherical and this is spherical, they will be in the same direction, but I just for clarity I am considering some angle between the area, the electric field here. The total area is equal to A, but for a very small segment here on this surface I consider it is dA, a small patch element or area element, and let theta be the angle between these two. So I can write that d phi, the flux, the d phi, and let me write E with it as for the electrostatics, then this thing will be equal to E times the electric field, it's the same on all the surface, so this will be E times dot dA, because we will have to represent the incorporation of theta there, because for the dot product I know that when theta is 0 we will get maximum of this thing, and when theta will be equal to 90 we will get minimum for this thing, or this thing will be equal to 0. And this implies that if we integrate both sides, then this is equal to phi e, the differential will be gone, and we will have integral on a surface. This may not necessarily be a closed surface, and this is equal to E times dot dA. And we will find that this thing is equal to E and dA and cos of the angle between these two vectors. So we will have E dot dA here. Now we know in spherical polar coordinates we have already calculated this thing, that what is dA, and dA over there we have calculated that dA is equal to r square sine theta d theta and d phi. And this one, when r square is constant and theta and phi are varying, then we are having our unit vector with this. And putting the value of E from here, so we will have phi E equal to integral on a surface and 1 over 4 pi epsilon naught q over r squared dot, this is our unit vector, dot r square sine of theta, d theta and d phi in our unit vector. So r unit vector, when multiplied with r unit vector, then we will get 1 here, and this r square will be, then means this goes with this one, and r square will go with r square, and we are left with